All right, so let's get started. First of all, I'd like to welcome all of you to my presentation about extending OPCUA to the field. I want to talk about the technical concepts that we are elaborating. I want to talk about the current status of the work and finally explain the further roadmap. Let me quickly switch off my webcam so you can concentrate on the content of my slides. And before we go into the content itself, let me first of all explain to you two terms that we are using when talking about extending OPCUA to the field. The one term is FLC. It's an acronym that stands for Field Level Communications, and we are using this term whenever we talk about the initiative and the related technical working groups of the OPC Foundation that are responsible for extending OPCUA to the field level in factory automation as well as in process automation. We have a second term. This term is FX, which stands for Field Exchange, and we are using this term whenever we name the technical extensions or the specification enhancements to the OPCUA framework in order to meet the diverse requirements for field level communications. So we name them OPCUA FX or UAFX as a short form for this name. Now, in order to extend OPCUA to the field level, I think it's clear to all of us that we have diverse use cases, diverse requirements to be met. So for example, we have to extend OPCUA to support functional safety. We have to ensure deterministic transport and real-time behavior of the networks. And we certainly have to cover all the specific application areas that we find in factory as well as in process automation, such as field instruments, remote IOs, or motion control, for example. And we have separated the technical work in two, let's say, phases or two categories. The one is the controller-to-controller use case. This is the horizontal communication, the connectivity between the different controllers of different manufacturers. And then the extensions of these concepts are then covering the controller to device, including device to device use case. And this is then finally bringing OPCUA to the various field devices. Now, the OPCUA FX specifications that we are currently working on, they have the part numbers 80 to 84. So it's actually 5 specification parts that first of all have the focus on controller-to-controller communications. These specifications are used on the one hand side now for the prototyping, but also in order to create test specifications. Furthermore, these specifications are laying the foundation for future specification enhancements to meet then controller to device and device to device use cases. Now with this slide, I want to explain to you the overall technical solution approach. First of all, OPCUA FX is based on conventional OPCUA technology, including client server, including publish subscribe, including the built-in security, the information modeling, as well as the DI specification part 100. The part 80 of OPCUA FX gives an overall introduction into this architecture. So this is helpful to get an overall understanding. We then have part 81, which is specifying the information modeling of so-called automation components and how to build connections between such automation components. In part 82, we talk about networking. Specifically, we describe how TSN is being integrated into the overall system architecture. We have part 83 talking about offline configuration. We have part 15 safety, which is an important element in order to cover functional safety. And finally, we have part 84, which is defining all the mandatory elements in order to create a concrete controller implementation. So it's mainly referencing to the various OPCUA parts, but also to external standards such as those out of IEEE. When we have a closer look at the key concepts, there is first of all the information model for automation components, which is specified in part 81. And we distinguish here an asset model as well as a functional model. And important is that by harmonizing these models, we finally have a uniform access to the information provided by the various automation components, and we become independent of specific controllers or device implementations. The asset model is describing the world of things. So these can be physical things like hardware or hardware components, but it can also be software, firmware, or even licenses. It offers nameplate information about vendor, product, firmware version, serial number, and so on. And it's based on the DI and asset management specifications, parts 100, 110. Important is that, as already mentioned, it allows the extension with existing companion specifications, and just to name one example, the PADIM specification for the process industry. We then have the second model. This is the functional model, also described in part 81. It describes the world of functionality. And this can be as simple as a digital input or digital output or a temperature sensor, but it can also be as complex as a servo drive with a lot of different input and output data, including state machines and including sophisticated diagnostics. Again, extending with existing companion specifications is important. You know that also the VDMA has elaborated a wide range of companion specifications that are complementary to the functional model we are elaborating for OPCUA FX. Another important element of part 81 are the so-called UAFX connections. These are connections built upon OPCUA PubSub in order to exchange data between functional entities. And these functional entities, as you have already heard, are part of the automation components. So by using these UAFX connections, any kind of process data can be exchanged. It can also include safety critical data and it supports the different existing security mechanisms of OPCUA, such as authentication and encryption. Very important is the so-called quality of service, which allows different types of data to be exchanged. Especially important is the exchange of real-time data, where we have to have a certain latency guarantee, a certain deadline guarantee. And this certainly therefore includes an underlying Ethernet TSN network for deterministic communication. As already mentioned before, offline engineering is an important element of UAFX. The concepts for this are described in part 83. The central element are so-called offline descriptors that describe the capabilities and the functionality of the automation components, also including configuration information and asset information. This offline descriptor is being used through the different life cycle phases of automation components. So it's been used in the development and the engineering phase. It's used in the commissioning phase, as well as during operation and maintenance. The concept is based on the Open Packaging Convention ECMA 376, and this means you can combine different files, different attachments in one single document. You can also build relationships to internal and external components, and it includes also digital signature. The information model is described using Automation ML, which is an IC standard 62714. And you see here on the sketch on the right hand side that the descriptor can not only include different information models, but also any other kind of attachments, such as manuals, drawings, and so on. Now on this slide here, you see how these offline descriptors are being used. First of all, by engineering tools that are importing these offline descriptors. Then the connection configuration is being created and generated out of the information that is provided. In the third step, the connection configuration is deployed to what we call the connection manager. And this connection manager is then managing and handling the connection configuration set. There's also the possibility to modify such configurations by system integrators in order to adapt a certain configuration, a certain installation in the shop floor, for example. On the slide here, you can see how the connection manager is then calling so-called established connections in the different automation components in order to set up connections between functional entities. Such connections can be between functional entities within one automation components or connections between different automation components. And the connection manager can be also part of a specific device. Like you see here, it's what we call the internal or integrated connection manager. There's also the possibility to have external connection managers that are then activating the connections in other external devices or controllers. Again, the connection manager calls the established connection, and then the connection is built between functional entities. This is completely flexible, so Also dynamically additional connections can be set up, like for example here between automation component 2 and automation component 4. So far I have mainly been talking about the base concepts of UAFX, including automation components, the offline configuration, as well as the UAFX connections. However, we are also working on extensions to these base concepts, and these have to do with device-specific or use case-specific models or protocols on top. For this, we have established different corporations. For safety, we are cooperating since several years with Profibus International, and for motion, we have established a cooperation with the ODVA and Salcos International. To quickly update you on OPCUA safety, we already have published 2 specifications. This is part 15 of OPCUA. In the release 1.04, we cover client-server communications and do not yet support real-time communication. In the release 1.05 that was published in November last year, we extend the concept also for publish subscribe. So this matches the UAFX requirements for supporting controller-to-controller communications. You see on the right-hand side the concept, which is having OPCUA safety built upon the underlying communication. We are using so-called OPCUA mappers to map to publish, subscribe, or client server, and then the safety data is exchanged over standard communication channel. This is also known as the so-called black channel. We have ongoing projects on the one hand side to create test specifications and a test tool which will allow us to test and certify safety devices, and we are also working on an implementation of a safety stack that can be used by companies for commercial products, but that will also be made available as open source. Future work is about extending to the use case controller to device, C2D. Especially we need to define how the parameterization is done in a safe way. With this slide, I want to give a quick update on the UAFX motion activities. The motion working group has been established in June 2020. The working group is elaborating the motion specification based on SIP motion and Salcos, and these existing concepts are changed and extended so that it fits to the OPCUA and UAFX system architecture, and it also supports the different use cases out of the IIoT and Industry 4.0. The first specification is currently in work, covering servo drives, so the closed loop drives, as well as frequency converters, also known as open loop drives. As I already explained before, the complete OPCUA framework and also the extensions defined by OPCUA FX are transport agnostic. That means they can be mapped to different underlying transport protocols and networks, including different physical layers. So I want to talk in the following a little bit about the importance of 2 technologies. Specifically, this is Ethernet TSN, time-sensitive networking, and the advanced physical layer. Ethernet TSN is an extremely important element in the overall technical solution approach because it supports deterministic communication over standard Ethernet hardware, but at the same time, TSN supports the so-called network convergence. This is allowing different IT and OT protocols sharing a common network infrastructure. For this, it's important that we define a common profile for TSN, and this is done by the IEC IEEE 6802 standardization group. In the context of TSN, I also want to mention the conformance collaboration that we recently established with other non-profit organizations. This collaboration is about developing a common and a single conformance test plan for the 6802 profile in order to ensure that 6802 compliant devices that come from different manufacturers that support different automation protocols reliably can coexist in a common and a shared TSN network. Further information you'll find by following the link below. A few words about Ethernet APL, the advanced physical layer, which is another key technology to bring OPCUA to the field level. Ethernet APL is two-wire Ethernet for the process industry that brings Ethernet also in hazardous locations. The technology launch was back in August 2021. Now first field devices and infrastructure components are available, and we are currently preparing our OPC Foundation certification lab to be able to do APL testing. This will be in a first step mainly about devices that have OPCUA as a second channel. So mainly using OPCUA for diagnostics and monitoring. But we have also first prototypes that use OPCUA as a native interface, also for exchanging process data. Now, after talking about the theory and the concepts that UAFX is adding to the OPCUA framework, let me talk a little bit about a real multi-vendor demonstrator that we have been realizing end of last year. You see here overall 17 controllers here in the upper part as well as in the lower part that are connected with each other using OPCUA and UAFX extensions. They are connected over a common network infrastructure that you see here in the middle section. This consists of Ethernet switches, Ethernet TSN switches, as well as of a 5G testbed. We are using two dashboards on the left and right hand side for the visualization, for the monitoring of all the communication and the different connections that have been set up. But we also use these dashboards to configure the UAFX connectivity between UAFX controller prototypes that then exchange process data with each other. Okay, talking a little bit about the roadmap for OPCUA specifications. We are currently finalizing the specification version 1, which has the focus on controller-to-controller communications. We plan to start the final member review end of May, and this includes all the parts that I was explaining before, parts 80 to 84. This is the so-called release candidate 3. We can expect a final and public release available in the third quarter of 2022. We are currently preparing for the kickoff about extending the concepts for controller to device, including device to device. This is the so-called specification version 2. The kickoff is planned for end of July at Schneider Electric in Andover in the US. And all OPC Foundation members are invited to participate. Okay, with that, I'm coming to the end of my presentation. I would like to thank all of you for your attention. I'm providing here some contact information as well as links in case you're looking for more information. And I want to also mention that we will organize a 2-day webinar, most probably in June, where we explain further details of the technical concepts, where we have our working group chairs, our technical experts, giving you a technical deep dive on OPCUA FX. Thank you again.